This is part 2 of the addition rule lesson. We now start with a definition, mutually exclusive events. Mutually exclusive events are two events with no outcomes in common. The probability that both A and B will occur is 0. An example is drawing an ace and drawing a king. I can never draw an ace and the king at the same time. If we have mutually exclusive events, we can use a special version of the addition rule, in which case the probability of A or B is equal to the probability of A plus the probability of B. For example, let's find the probability that a card chosen at random is a spade or a heart. Well, I know that these are mutually exclusive because a card can't be both a spade and a heart at the same time. The probability of a spade is 13 over 52. The probability of a heart is also 13 over 52. Since they're mutually exclusive, I don't have to find the probability of both. And to find the probability that something is a spade or a heart, all I have to do is add those two probabilities together. 13 over 52 plus 13 over 52 makes 26 over 52, which simplifies to 1/2. Now let's try a slightly different problem. On any given night, the probability that Nick has a cookie for dessert is 10%. The probability that Nick has ice cream for dessert is 50%. And the probability that Nick has a cookie or ice cream is 55%. What is the probability that Nick has a cookie and ice cream? Well, we know the probability of a cookie is 10% or 0.1. We know the probability of ice cream is 50% or 0.5. We also know the probability of a cookie or ice cream is 55% or 0.55. This problem is different because we are looking for and. We're trying to solve for and. Let's plug everything into our formula. We start with the probability of A or B, which would be cookie or ice cream, so 0.55, equals the probability of A, which is cookie, so 0.1, plus the probability of B, which is ice cream, so 0.5, minus the probability of A and B, which we don't know, so there's our x. Now we solve this. Add together the 0.1 and the 0.5 to give us 0.6. And now there are a couple ways you can solve this. I personally like to add x to the other side. Then I get x plus 0.55 equals 0.6. Subtract 0.55 off of both sides. And x equals 0.05, which means there is a 5% chance that Nick will have both a cookie and ice cream for dessert. So now try this one. Your dad only ever makes one meal for dinner. The probability that he makes pizza tonight is 30%. The probability that he makes pasta tonight is 60%. What is the probability that he makes pizza or pasta? All right, we know the probability of pizza is 30% or 0.3. We know the probability of pasta is 60% or 0.6. The probability of pizza and pasta is 0 because your dad will make one meal for dinner. He's not making both. So now to find the probability that he will make pizza or pasta, since these are mutually exclusive, I just have to add them together. 0.3 plus 0.6 makes 0.9, which is 90%. There's a 90% chance that he will make pasta or pizza. Now another one to try. After your little sister has gone trick-or-treating for Halloween, your mom says she's allowed to have 2 pieces of candy. The probability of her having a Snickers is 50%. The probability of her having a peanut butter cup is 60%. The probability of her having a Snickers or a peanut butter cup is 100%. What's the probability of her having a Snickers and a peanut butter cup? So let's start with what we know. We know the probability of a Snickers is 50% or 0.5. We know the probability of a peanut butter cup is 60% or 0.6. We also know the probability of a Snickers or a peanut butter cup is 100%, which is 1. So now we plug these into our formula. Probability of OR goes first, so 1 equals 0.5 plus 0.6 minus x. And now we solve. 0.5 plus 0.6 makes 1.1 minus x. Let's add x to the other side. We get x plus 1 equals 1.1. Subtract 1 off of both sides, and x equals 0.1, or 10%. There's a 10% chance that your little sister will have both a Snickers and a peanut butter cup. All right, we're going to look at a slightly different problem now. A recent study of 200 nurses found that of 125 female nurses, 56 had bachelor's degrees. And out of 75 male nurses, 34 had bachelor's degrees. How many nurses are female or have a bachelor's degree? So this question is different because it just says how many. It's not asking for a probability, just a number. Let's start with what we know. We don't need to worry about the 200 total. We know the number of female nurses. So if you see this N out front, that's just the number of something, is 125. We know the number of female nurses and they have a bachelor's degree is 56. We also know the number of males is 75. And the number of males with a bachelor's degree are 34. Now we are looking for nurses that are female or have a bachelor's degree. So following the same logic as before, my apologies. To find the probability or the number of females or bachelor's degrees, we're going to start with the number of females. That's 125. Add on the number of bachelor's degrees. But we don't actually know that. The number of bachelor's degrees is actually the female bachelor's degrees and the male bachelor's degrees added together. So that'll make 90. So we add 90 minus that little bit of overlap. So that is our females with bachelor's degrees. So 56. 125 plus 90 minus 56 makes 159. 159 people in this study were either females or had a bachelor's degree. You try this one. 135 people were asked, 78 said they like dogs, 45 said they like cats, and 32 said they liked both cats and dogs. How many people like cats or dogs? All right, to do this problem, let's start with what we know. We know the number of people that like dogs is 78. The number of people that like cats is 45. And the number of people that like dogs and cats is 32. So now to find the number of people that like dogs or cats, we take dogs, which is 78, plus cats, which is 45, minus that overlap, which is 32, and we get 91 people. 91 people in this survey like cats. And now it's time to practice.